We're talking MapReduce today. I've got some slides. It's kind of planned to be mostly me talking, although I'm hopeful we would have a lively conversation, one way or another. Quite frankly, it's pretty boring to make simple slides. So I've made fairly advanced slides, and let's see how deep can we go. I'm assuming we're all familiar with how MapReduce works behind the scenes. It's this data warehouse grade crunching framework, crunching paradigm, where you have the map phase, the shuffle phase, and the reduce phase, and both the input and the output are presumably large collections of key value pairs. So the first important part is that every bit of input is not just a data element, it's the key and a value. The second important piece of input is that, generally speaking, the input data is sharded. So it's not, you can have a trillion keys and you would have like tens of millions of shards. Usually shards would be approximately 64 megs, just because that's consistent with the size of the distributed file system shard, which is, I think that's a standard in HDFS. It's a standard in some proprietary systems I'm aware of. It's overall a good number, 64 megs. I will not cover what can you do to use MapReduce in the cloud today, because there are so many tutorials on that, and there's a good chance you would never ever have to answer this question in your life. If you're an architect at the level where you have to make the decision on which one to use, well, we can talk separately. And I do not plan to cover the interview questions that are often asked about MapReduce, because again, there are just so many questions out there, and they are, quite honestly, they're either super tricky and sneaky, as in they need an aha moment, or they are fairly basic. My goal for the meetup, as always, is to present the ideas in a way that, if all goes well, by the end of the conversation, all of us will be able to design MapReduce from scratch and prototype the first implementation. So my favorite setup is, imagine you're transported back in time to where there's no MapReduce. And so there's no MapReduce, but there are the tasks to be solved by MapReduce. So you could say, hey, I know something. And then ideally, they trust you because you can explain yourself well. You build it, and it changes that world for the better. I'm loosely breaking this down into 3 sections. I would like to talk about theory, because it's interesting. I would like to talk about some implementation details, because honestly, in my book, I'm slowly changing into the infrastructure engineer in the past couple of years. So in my book, MapReduce is mostly interesting because it's a really genius implementation, especially at the time when we didn't have SSDs. During those times we had spin disks where reads are fast, but seeks are slow. And the original MapReduce implementation was really well optimized for this particular use case. And I think it's important that we actually talk about what is MapReduce used for, because honestly, when I look around, there is a standard example of using MapReduce to count the number of occurrences of the words in a text corpus, which is the most boring example I've ever seen. Nobody ever does this in our lives. If you ever need to count the words, you can pre-compute those, or you can have inverted indexes. So you just look for the word by its key, and the first thing you get once you get to the value for this key is the size of the collection. So it's super boring. I'm trying to come up with more real life and more complicated examples, while at the same time I'm explaining why exactly are they useful. Yeah, full disclosure, I wrote at least 100 MapReduces myself, not to mention like the real ones, the real mappers and real reducers, not to mention the indirect use cases where I know the underlying machinery is using something like a MapReduce, but of course it's not exposed this way. Quite honestly, I think most of us by this time have done something similar. All right. I'm going to start from practice. Let's skip this counting word exercise. It's, as I mentioned before, it's a poor example. One frequent use case of MapReducers is when you need to visualize or present some data. Every single time you need to have some diagram or bucket in, most often you would probably want to use this sharding key, the breakdown key, as the output map key, which is the input reduce key. So the bottom line is, so imagine you need to just build a histogram. Let's say you want to build a histogram of, I don't know, ages of people. Well, quite frankly, you would not need a MapReduce there, because if you just break down ages by even months, it's just a really small number of buckets. So it's not really showing the power of MapReduce. You just go through your data in parallel, which is effectively map shards, and then on each map shard, you keep something in memory, some data structure per the shard. Then once the map shard is done, you exchange the data structures or just write them down somewhere. And then you have the second phase, which is effectively the reduce phase, which reads all those data files and gives you the final histogram. The fun begins when you actually want to prepare the larger histogram across multiple dimensions. So if you just have age, that's simple. It's a few dozen, 100 buckets. If you have 10 dimensions of 100 buckets each, and you want to have the interface that allows you to quickly sub-select some sets of dimensions, clearly you would not be able to build a data structure that lets you do it on the fly. So what you would do is you would pre-compute a still large but smaller aggregate data structure, so that you can query this data structure later on once the user would like to select the right dimensions or filter more. It's this OLAP cube idea. And in this regard, what you would do is you would take all your terabytes and terabytes of data, you would put this multidimensional bucket as your output map key. So clearly what would happen is that if you have, let's say, a terabyte of data in the input, once you have the map key as your bucket ID, you would have the same terabyte of data in the reduce phase. It's not always the case that it's one-to-one mapped. In this particular case, it will. But within each histogram, within each cell of this multidimensional bucketing, you can perform some collapse of your data structure. You don't need to keep every single data element. You probably want some counters, some averages, some representatives, some way to quickly access this data if you store it somewhere. But this huge data structure, which is terabytes of data collapsed, can just be stored in single-digit kilobytes. And that's the result of your reduce phase. That's effectively MapReduce in a nutshell, because your map phase looks at every single data element. You can safely assume they are in a random-ish order. You can't really make assumptions about in which order do they come in your input. Then in the map phase, the reduce keys, the shard keys, are assigned. The output keys, as I call them, are assigned. And then clearly for each individual cell, the ultimate collapse function is the reducer. So that's my second example, which loosely maps to group by, if it's a SQL term. The third class of examples is, again, in SQL terms, what you would do using a join. So if you really need to compare or cross-reference multiple data sets, you probably want to use some join key. I used emails here in the example because I want more emails. So maybe you have multiple marketing campaigns. Your company just merged with a larger, different company, and you want to make sure that, hey, can I see if the users share some spending habits or shopping patterns? That's a fairly big job. But if the key is, let's say, the email itself, you can argue that email is a bad join key because you would like to join by user IDs. But for production data sets, I would agree. For analytical data sets, if you're a data scientist, that's a good first step, to just join by email. And machines are cheap, data is cheap. If you're not going to production with sub-millisecond latency SLAs, you can just use emails. So clearly, if you need to join two data sets by email, the email itself would be your reduce key. And then the reducer would look at everything you see about this particular user from about this particular email from all your input data sets, and has some logic that combines, again, collapses one or more input data points into a single aggregated result. After practice, I actually wanted to go into implementation. So again, in my head, in my mind, the genius of MapReduce was not the idea; it's how it was done originally. It's fairly tricky to explain from the ground up, and I think one of the better ways to do it is to think of forget the cluster, forget the data center. Think of a single machine with a huge number of cores, so 1K cores, and let's say the storage. I'm hesitant to say the hard drive. So just some storage attached to this machine is petabytes large. So you need to crunch hundreds of terabytes of inputs and produce up to hundreds of terabytes in outputs. This is what I call the data warehouse pattern. By the way, this question is asked pretty often. What is a data warehouse pattern? It's the way I usually ask this question on the interview is, so you're saying BigQuery is a SQL database. Can you build your service so that BigQuery, Google's BigQuery, is your backend? That's a simple question. The answer is no, because BigQuery is not designed for frequent updates. It's not real-time updated. It's designed for huge batch updates, because fundamentally behind the scenes, it's a bunch of read-only files. It's read multiple times, written infrequently. Multiple doesn't mean it's serving this data as the per request basis. Read multiple times means a bunch of crunchy jobs would aggregate, slice and dice every single input bit of data in tons of different ways. That's a data warehouse pattern. So imagine you want to build a data warehouse ish solution based on a single super beefy machine, imaginarily. Well, what you're spared from is you don't need to worry about network throughput because it's all on the same machine. And you don't have machines dying because it's either this machine is dead or it's alive. However, the main challenges still persist. You need to worry about how to use the CPU, all the CPUs. You need to worry about how to make sure you use the RAM effectively. By CPU usage, what it almost always boils down to, if it's a multi-hour job, multi-hour as in wall time, multi-hour. When you count in CPU time, multiply this by the number of machines and/or cores. So multi-hour here would be tens of thousands of hours. By optimizing CPU usage here, what people mostly mean is making sure all of them are loaded. It's not hard to have the peak CPU utilization to be at 100%. For example, in the middle of the map phase, once all the workers have started, they have their disks synced, they have whatever they need in memory. In theory, it's not hard to reach every single CPU load at 100%. But then shards are of uneven sizes, CPUs get warmed up unevenly, some of them get slower, some of them get cache misses. So at some point you end up in a situation where the majority of the CPUs have done their part of the job, and they're just waiting for the others. Or you have some clever algorithm which can somehow orchestrate more tasks to be performed by these now idle CPUs. That's what I mean by improving CPU usage. And for the RAM disk balance, the challenge is, of course, to make sure that you do use RAM as well as you can. But if you put everything in RAM, it's not going to work. In the best case scenario, your swap system would kick in and it would be super slow. In the worst case, you just kill the machine. So both these challenges are non-trivial. As it always happens, in any particular case, in any specific case, you can actually win a lot by just optimizing away for this particular use case. For data warehouse kind of patterns, kind of queries, MapReduce offers a fairly universal approach that is doing a good job in the vast majority of cases. So it's really useful to just be aware of how it works. Before we get there, a bit of theory. I'm assuming I don't need to talk about what map is and what reduce is. But, well, I guess just in case for anyone else who's listening to this and is not familiar with the concepts, they both come from functional programming. They existed for many, many years. Functional programming is by itself a fairly advanced topic, and people can even disagree on what functional really means. As in, the classical definition of functional programming is that functions must be the first-class citizens. but then most modern languages, including JavaScript, will suddenly be functional languages. The way I use this term mostly is functional programming is the programming paradigm where everything is immutable and you need to implement. The way you code, the way you write your program is a bunch of operations that transform the data in some sequence, so that even though in theory you don't have any variables, you don't have any change in state, eventually your program is purely take A as an input, produce B as an output by means of a certain series of transformations. And this paradigm puts a lot of emphasis on type systems, on type invariants, and in practice, of course, it's a lot further from modern computer architecture, so it's fairly hard to optimize functional programming in general. But in terms of the mental model, it allows, because it's pure, because functional functions don't have side effects, it's always input into output. It's a lot easier to reason about functional constructs. So, seen in this regard, map is a fairly straightforward functional operation. If you don't feel like speaking functional programming, you can think of map as transform. As in, you go through an array, you say for each, you change each array element, maybe you create a new array. So if your input array had elements A, B, and C, and you want to map it using function f, you just create a new array that contains f of A, f of B, and f of C. In the functional meaning of this word, since f is a pure function, the order of evaluation doesn't matter. If for example, if f of A or f of B or f of C brings something to the screen, clearly you probably care about the order in which it happens. But in the functional world, you totally don't have to, because there's no way they can possibly produce any side effect output. If they do, they would need to have different type signatures and sequenced a certain way so that they can use a terminal or whatnot in certain order. So basically, they are stateless, pure functions. And map is just an operation that takes one collection of elements. I don't think they use the word array in functional programming. I certainly don't. But basically, you take one collection of elements and you transform it into a different collection of elements. In the MapReduce setting, you take input elements, which are key value pairs or just values. The input keys don't really matter unless you want them to. And you produce each input element once it enters the map phase. The mapper, so the user-defined logic, can produce 0, 1, or more key value output pairs. And they may have different keys. They may have different keys, or they may have repeated keys. And repeated keys are not the same as the same key multiple times. So same key, different values is effectively multiple key value pairs with the same key. It's important for shuffle and reduce phases later. That's, in a nutshell, what map does. Quite honestly, if you don't have the reduce phase, you don't need to invent anything particular. Map will just be take your input. Let's say it's stored in a bunch of text files, and each data record is one line of the text file. You could write a bash script that just takes your directory, go through all the files, performs a certain operation on each file. This operation being read file line by line, write another file with each line being the result of processing of each of the input line into 0, 1, or more pairs of output key value pairs. That's your map phase. The interesting part gets between the map phase and the reduce phase. So that's a shuffle phase. Before we get there, let's talk about reduce. Reduce is an even simpler functional operation. If you speak C++, it's effectively accumulate. If you speak Haskell, it's effectively fold, although Haskell has reduced by itself. Reduce just means take a collection of elements and reduce them into one. The collection of elements has to have the same type, and the one reduced element can have a different type. So the simplest example of reduce, actually, the most commonly cited example would be, let's just sum up those numbers. So for example, if you're looking at the number of occurrences of each term, then the map phase just splits the text, takes each string or each document, splits it into words, emits the pairs where the key is the word and the value is 1. So then the shuffle phase would put all the identical words together, and the reduce phase would need to sum up a bunch of ones to get the final number. It does not have to be the case. You might as well have a more complicated data structure for the reducer. My favorite example, which I used a lot, would be compute some statistics. Since I've been doing machine learning for a while, if your reduce key contains a bunch of numbers, your reducer output may contain something like mean, standard deviation, skew, a bunch of percentiles computed in some pseudo-approximated fashion or whatnot. That's a standard legal appropriate usage of the reducer. So the tricky part is what happens between the map phase and the reduce phase. And to explain it, let's keep in mind we're still thinking about this single machine with a bunch of CPUs, to keep it simple. Forget the map phase for now. Let's say we have the data pre-mapped. Let's say we could afford to just take the input of a few hundred terabytes in our petabyte huge storage. So take this input, crunch it with some simple single pass sharded solution, and we'll have another few hundred terabytes of mapped output. This mapped output contains a bunch of key value pairs. The shuffle phase, what it would do, it would first of all group the elements by key. So you would have a bunch of reduced shards. How are they created is a different, quite honestly, a separate conversation. In practice, they would just be the number of machines you have, more or less, and then divided evenly or assigned later. But in practice, for every single key, you would have a reducer. If you speak in Java or C++, your reducer class would be instantiated for every single unique key in your mapper output. So if we get back to the example of counting the number of word occurrences in the text file, the reducer is called once for each unique word, and it is being fed every single counter. If it's just counting every word once, it's just going to be fed a batch of ones. You could do some pre-aggregation, so it's maybe your map phase could be just a histogram of word counters per big document. So many of those would be numbers greater than 1. Doesn't really matter. What matters is that for every single unique output key, you would have the instance of a reducer created. And clearly, this phase cannot be parallelized. You will have this reducer running on a single machine. So what MapReduce, or what the shuffle phase does between map and reduce, it needs to group these data points by the output key, but it also needs to sort the values. That's also important. Most implementations I'm aware of have this notion of secondary key, so you don't need to actually sort them by invoking comparisons on the actual results. But effectively speaking, in implementation language, is just optimization hints. In the theoretic meaning of this word, all you do is you sort this potentially huge sequence, huge collection on the fly, because you don't need to have it pre-sorted in full when the reducer starts running. Once you know, if you have, let's say, the reduce key, which is a gigabyte of data, once you know the order of the first 10 megabytes, you can already start reducing. That's another secret sauce of MapReduce. As soon as you know you can start reducing certain key, you can start doing that. That's why it's important that the reduce phase cannot possibly start before the whole map phase is completed, because you never know which output key can the remaining map shard generate. Back to the word counting example, if you have certain word with just 1 or 2 occurrences, and you have 99.99% of the input data corpus crunched, you cannot have the guarantee that in the remaining few documents you don't have this word. And if you start reducing before the map phase is completed, you may need to restart that, which, by the way, is okay, since everything is supposed to be reproducible. So it's another possible optimization. Just keep in mind that it has to be sorted. It's part of the shuffler, and it has to be sorted online, in a sense that you don't need to have the whole data structure sorted in memory or whatnot before the reducer can start. You just need to have this iterator that would feed the reducer all the data in the sorted order. Now, am I making sense so far, or is it super complicated? Mm. It depends on whether your reducer uh, is agnostic to the order of values it receives. If it just taken the sum of the elements, or maybe the mean and standard deviation, then your reducer is, well, if you have this huge list of elements to reduce, if you can afford to put parentheses in any order, you might as well do it in parts. You might as well do it in chunks. In practice, because some reducers do not have this property, order matters. In practice, the issue happens when one output key is huge. So maybe if you count in the number of word occurrences, the word "the" is so popular, and you would wait for this key. So if you know your reducer can be agnostic to the order, what you would do is you would just create a few artificial keys. The word "the" would have different keys: the1, the2, the3, etc. The underscore hash of the input document, and then you would have the final reduce or reduce phase. But in most cases, well, that's an overstatement. In quite a few cases, you actually need to rely on the order of these elements. One good example would be if you want to select top 3. So if your reduce phase just selects the first, not just the random 3 outliers, the random 3 data points, but the top 3 by some metric, what you would do, you would put this metric as a secondary key. Probably you would put this metric negated as a secondary key, because the sort order would be ascending. And then your reducer would just look at the first 3 or first 10 or first 10,000 and throw away the rest. Well, in this regard, you clearly cannot possibly assume that two reducers can join their results. Of course, you can write some clever piece of code that creates 10k elements on both and then joins these lists and keeps 10k out of 20k. Again, to me, this is optimizations. MapReduce by itself was not designed for this kind of optimizations. In practice, by the way, you win more by optimizing on the map phase, not on the reduce phase. If you have the map machine that crunches through gigabytes of text, and again, consider this word occurrences as the example, maybe your mapper shouldn't output a bunch of key value pairs, each word, comma, 1. Maybe you can group them by the document and say, hey, in this document, I have the following histogram of counters. Or you can take it one level further and say, I don't even group by documents. I group by the whole gigabyte of data I've consumed so far. Because clearly for the word occurrence histogram, it's irrelevant from which document did certain word come. What matters is the total sum of the counters. That's this combining of the data points before they leave the mapper is another useful optimization. My primary goal here, so let's get back to basics. My primary goal is to make sure we understand MapReduce to the degree that we can re-implement it. If we ended up in Google of 1999, or more like early 2000s, and we need to crunch something in the index, knowing how Shuffle works and knowing how Shuffle helps connect map and reduce both in the theory/algorithm space and in the practice/infrastructure space. This knowledge is the key part. The rest are details. Okay, next slide, I guess. So when it comes to squeezing the most out of the performance of the final system, as I said before, it's all about making sure no CPU is waiting, no tasks are waiting. In practice, oftentimes you don't just have one MapReduce. You would have a sequence of those. Or more likely, you have a cluster. You have the data center that can run MapReduces for multiple users. So when some machine is idle, You can load its CPUs with map/shuffle/reduce shards of other tasks. If you just have a single MapReduce to run, the biggest pain is to wait for the last final map shard, and then for the last final reduce shard. That's a real life pain. I've seen it first-handedly multiple times. It oftentimes happens when it's like Windows copying files. Honestly, it gets to 99%, and then it's stalled for another half an hour because that one map shard or one reduce shard needs to crunch through all the data points. It's all right. That's how it should be. Oftentimes there's not much you can do. You can try to even up your shard space, but there's only so much you can do. If you have, I'll get further down the road. I'll mention how MapReducers play well with data warehouse SQL-ish queries. But in a nutshell, if you have a complicated data collapse job, I use the word collapse a lot. It's because I'm used to that. When you have some reporting query at large scale, effectively in my head, in my vocabulary, in my language, it's called index collapse. Index collapse is when you have a search index, which is pretty much web index, and you want to collapse it in some way to a more condensed format. So if you have, for example, at my job right now, we have tons of data on certain poker hands, for example, and you want to collapse this data in certain format to produce some report. So when you have this collapse job, you can think of it as 100-ish lines of heavy SQL. If you were to run this query on the actual SQL database, which is quite painful because SQL is designed to be real-time, update frequently. But if you were to run this query on a SQL database, it would just optimize the query, hit some indexes, and produce the result. If you were to run this on the data warehouse, which is update not too frequently and query heavily, multiple queries, it would effectively compile into a series of MapReducers. It would compile into something that has to do with map shards. Somehow internally it would do shuffle and sort. Then it would do reduce phases. The difference is that unlike the canonical single MapReduce job with just 3 stages, map, shuffle, and reduce, when you compile a large query into a bunch of MapReduce jobs, let's say take Hadoop. HiveQL is a query language, which is very similar to SQL. I think it is SQL. And HiveQL queries are compiled into Hadoop MapReduce jobs. What would happen is, for example, a single mapper output could potentially go to more than one reducer. So these reducers can be parallelized as soon as the mappers are done. Or, which is even more frequent, the output of a reducer becomes an input to a mapper. And since all mappers are independent, once some reduce shard is done computing, the map shard for the next step can already start computing its own things there. And since ideally the ultimate sharding is changed between steps, this rebalancing of load happens behind the scenes, so that the machine that was busy, the shard that was taking the longest, the slowest shard in the first or the nth stage of the process would not be the slowest one in the n+1st stage. So it kind of balances out, more or less. Another thing that I have to mention is that the original implementation of MapReduce was really famous for mostly being optimized for the spin disks, so the actual hard drives with heads. And these days, in 2021, we live in the SSDs era, where we're almost used to the fact that SSDs are cheap enough and fast enough, and we just use them everywhere. Actually, I think it's safe to say we're entering the NVRAM era, where you can just use non-volatile RAM. Back in the days, SSDs were non-existent or expensive. And even in the early stages of SSDs, in the early years of SSDs, SSDs win because the seek time is almost negligible. It's non-zero, but it's almost negligible. But most people mistakenly used to think that SSDs are just a lot faster. That's not true. In fact, reading from a spin disk sequentially is extremely fast. It's comparable to reading from the main memory. It's just once you need to do a seek, you're screwed. Or once some other process needs to do a seek, you're screwed. So what Jeff Dean and Sanjay at Google did a good job with is making sure you don't need to seek that often. If you think about it, it doesn't sound too hard. For example, if you do the shuffle phase, if you perform the shuffle phase in large bulks in memory, then in order to perform the actual sorting, all you need to do is to join a bunch of streams that each subpart of the stream, each shard of the stream, is already sorted. So it's the merge of a bunch of sorted lists, which can be done with a single seek of every single list, assuming they are on different machines. So this kind of tricks allowed the original implementation to be fast, and what is also important, to not put too much load on hard disks, because they tend to fail if you seek too much. So instead of hearing this ugly constant seeking noise of hard disks slowly dying, you would walk into a data center and hear a smooth, monotonous, high performance, high throughput reads and writes on the hard drives. Well, I didn't hear it myself, but I saw it on the dashboards, and that's how it should be in a good MapReduce job that is running efficiently. Next, I wanted to talk more about the practical use cases. As I just mentioned, SQL-like queries can be converted into MapReduce queries. I'm not saying it's perfect, but it was good enough for the 0 to 1 step. And honestly, it's not hard at all. Every single time you have a join, you need to have the map phase. So once you have the join key, you know this join key would be the shuffle key and the reduce key. So it has to be the map output key. Every time you have a group by, again, it has to be the map output key / shuffle sort key / reduce key. When you need to filter something, well, if it's filtering on the input, you can do it on the map phase. If it's heaven, clearly it's on the map phase. If it's where, well, if you filtering on the calculated fields, it has to happen in the reducer or the next stage mapper. And once you have a sequence of map reducers, it's clear. By this point, it should be evident that if you have a sequence of map reducers, you can easily move some logic between the reducer of stage n-1 and the mapper of stage n, because the sharding is the same reduced key, the same output key in certain stage, which has been reduced upon, effectively becomes the input map key for the next stage. So you could balance some load, or you could even perform multiple reducers in the first MapReduce to prepare data in one pass for different inputs on the second stage, on the consecutive stages. And this part we covered. Now the tricky part. Another person I spoke with before this conversation, he wanted to hear more about failover, dealing with failed workers. So we're getting there shortly. How do you store the input? Well, I promised to start from SS tables. SS table stands for sort a string table. It's incredible how much can you do if you have the primitive that is just an effectively implemented disk first data collection with the means to iterate over it. In fact, I'm not sure how much into the details can I go here, because it's proprietary, but fundamentally, even real-time databases such as, well, actually I can, yeah, even level DB, which is a single shard big table, even level DB internally uses sort of string tables. They just get obsoleted and removed on disk in some background fashion. So most of the times, if you get transported back in time to pre-big table, pre-MapReduce times, you would need to reinvent sort of string tables that are disk first, persistence first, and easy to iterate over. And you will. It's not hard. A friend of mine, my first machine learning teacher. I have two machine learning teachers in my life. This is the first guy back when I was at the university. I think when he joined a big company eventually, they didn't have MapReduce. They just had load balancers. So as a joke, he built something called BashReduce, which was MapReduce over text files using Bash, Netcat, and Makefiles. Nothing fancy. You just need to. If you do it this way, storage schema and network transport become more important because there's only so much you can do with core utils in Unix systems. But it's not impossible. So the bottom line is, chances are you would use some kind of distributed file system, which you covered in one of the previous episodes. Chances are your shard size would be in the order of 64 megabytes. Honestly, I did look into this in the past 5+ years. I would not be surprised if this number has changed. But back in the day, it used to be 64 megabytes, and every Hadoop tutorial I've read through uses this magic number as a shard size. And of course, there's this mantra of moving code to data as opposed to data to code. So ideally, you would have your data available at high speed at your compute engines from some locally connected hard drive. And data locality is important for performance, even if you cannot afford to assume that your data is stored near to each machine on its own hard drive. You would probably win a lot by making sure that every single data center rack has at least one machine with this data, because, well, inter-data center network traffic is free, but still you can possibly saturate it. Intra-rack traffic is free and it's really hard to saturate. So if a single rack has one machine, the hard drive of which has this data file, it's fairly quick to access by all other machines on this rack. Now for the tricky parts. It's awesome that we have this mapper logic, shuffle logic, reducer logic, but they need to be orchestrated somehow. The standard solution is to have, well, surprise, an orchestrator, which is just a dedicated machine, the job of which is to make sure that once we know the size of the input data and the breakdown of this input data into files/shards/keys, it would assign chunks of work to different mapper machines, which have identified themselves or have been pre-assigned as mapper machines for this particular MapReduce job. It would restart whatever has failed. It has some logic that, well, not all MapReduce jobs are successful. Sometimes the user code has bugs. Maybe you divide by 0 in some particular data point in a certain map shard. So in practice, this orchestrator would make sure that, hey, if somehow the map shard is failing in one machine, try it again on a different machine. But if it fails 3 times on 3 machines, probably you want to finish this job with an error and notify the users that, hey, your MapReduce failed. Your mapper has segfaulted on certain shard. Please investigate. We've tried this 3 times. In practice, since MapReduces are so widely used, or at least they used to be so widely used back then, you would have decent debugging tools. It would just tell you to which machine under which username can you SSH, so that you could look at your code live if you would like to. And at this scale, hardware bugs happen, network issues happen. So you have to be pretty resilient with respect to something failing on one run and succeeding on the second one, on the next one. And of course, it's really embarrassing if the orchestrator dies, because if the MapReduce runs for multiple hours on tens of thousands of machines, you don't want to lose this. Well, we today know that the best solution here would be to literally elect the orchestrator. So you would have 3 or 5 of those with some Raft Paxos cluster. So if one of them dies, the other ones take over. But again, this is actually not that essential, because I wouldn't say the orchestrator is stateless, but it doesn't perform many mutations, because the shards don't talk to it on every single minor thing they do. They just report on the progress, and they ask for next pieces of work to do eventually. So if the orchestrator dies for a moment and another one takes over from some snapshot that was taken a couple seconds ago, most often you won't lose any work. So your goal is to not redo nothing. Your goal is to make sure you don't lose the progress, and you won't. Yeah, one thing I have to mention too is in a functional programming paradigm, mappers and reducers must be deterministic, since they are supposed to have no side effects. In theory, if you're running some really important job, like you're computing some space mission trajectory or whatnot, with humans involved, you may want to double check yourself. So the orchestrator can be told, or can be designed so that it can be told, to redo every single map shard and every single reduce shard a couple times to just compare the results to make sure they match. So that if one CPU is buggy, I remember the times where it happened. Some CPUs had hardware issues and they would multiply certain numbers the wrong way. So this would be caught by making sure the checksum is the same. And if you are unaware of this and you would like to maybe have some histogram in multidimensional space and return just 10 random elements, 10 random. So if your reducer returns 10 random keys, 10 random values for a given key, if it's pure randomness, it's not reproducible. So this kind of check will fail. Back in my days, it was not advised to do it this way. You would probably be asked to use pseudo-randomness by hashing the input somehow and then replacing random by top 3 by certain hash. Or you could set a flag that, hey, I'm actually consciously using randomness, so don't try to run this multiple times, and if it's rerun, just use the latest run. I don't care about the result. That's the advanced part of what I wanted to talk about, and honestly, that's it. Did we finally make it short? I'm positive you guys have questions. I have zero knowledge about SETI, but I can tell you that at CERN, they use something very much like MapReduce to parse the collider experiment results. But again, on the implementation level, there's no such thing as converted to MapReduce format, right? As long as your data is somewhat sorted, so you can read it in a sorted fashion, you're good to go. And if you need to process tons of data, chances are it is sorted. So I think in terms of, I can answer this. I can answer this from the architectural standpoint. I can imagine some architects in SETI or in CERN or whatnot gathering together in a room or over beers or whatnot, over Zoom if it's 21st century, and talking about, hey, we need to run certain kinds of crunching jobs. Let's transform our data to the format which is more suitable for running these jobs. But I can bet money that in 10 hours of these conversations, 9 would be spent on deciding which proprietary format to use, because each of those is a lock-in into something. So the actual conversation would not be how do we make our data MapReduce friendly. The actual conversation would be which MapReduce provider do we choose? Do we build one ourselves? If we choose something, do we use the modern version, the new version, or something that is slightly more outdated but somehow more reliable and all that? So that's the best answer I can think of right now. Great question, by the way. All right then. Well, let's declare this advanced MapReduce tutorial successful. Thanks, everyone.